All right. Hello, everybody. Welcome to Calculus 1. My name is Professor Niazi. We'll be briefly going over the syllabus, and then we're going to jump into the material right away. So here's some of my personal information and contact information. Here's a course description. The textbook is free and it's online. You can access it by clicking on these hyperlinks on the syllabus, which is on Canvas in the syllabus tab. Your grade will be determined by the following criteria: 30% homework, 40% tests, and 30% your final exam.
So
you'll be taking your exams during lab period, and apparently you guys already had lab, right? Good. Okay. So that's good. Those will be the periods in which you guys will be taking the exams, and I'll be proctoring them during that time. But whenever you guys have actual labs to do, you'll be doing that with Dr. Zoller. Okay, here's some course policy and guidelines. No technological devices will be utilized during class unless otherwise permitted. So laptops, cell phones, iPads, iPods, everything gone. Everything, and I don't want to see it ever during class. One thing that I will make an exception for is a calculator or something like that, but typically we won't need that very often. So, but you could bring a calculator, that's fine. Harrison over here knows my policies, and as you can see, he didn't have any technology out. He knows what I think about technology. Yeah, no computers, no laptops. The good thing is lectures will be recorded. So if you're striving to record notes or whatever, you'll be able to rewatch what happens in class over and over again. You can pause it and rewind it and replay it. So there's no reason to be, worried about, well, what if I miss a detail? In today's day and age, the silver lining of what's going on is that we record lectures now. So that's pretty cool. So you don't have to worry about making sure you get every detail down, all right? You can always rewatch it. And I'm fine with you guys utilizing a pencil and paper or a pen. Here's some other statements that you can read if you like. Over here is the schedule. It's a very tentative schedule. We'll see what we'll be able to pull off here. As you can see, today we have class, but on Monday, it's Martin Luther King Day. So no class, no campus, I believe, is closed. But I will upload the next section. So be prepared to watch it on Canvas, and I'll send out an email about that. Okay. And that's about it. Let's get started because I don't want to spend too much time on the syllabus. We have lots of mathematics to learn. Okay. So let's talk about tangent lines. Let's say you have some arbitrary function, f of x. We can find the tangent line to some point, right? What is a tangent line? Many of you might know this. Yeah, it's a line that will touch the function at exactly one point and exactly one point only. Okay, so you guys are familiar with that concept from the past. However, you'll see that this concept has some frailties, if you will. What if you have a function like this? And we want to know what is the slope of the tangent line here, or what is the tangent line to this point right here? Well, notice that Now it's touching many points of the function, right? And, you know, I know what you're saying. Well, yeah, but why don't I just put a line like this through it, you know? This will achieve what we wanted. It will just touch it at one point. But guess what? Such a line would have infinite slope, right? Vertical lines have infinite slopes, so that can't work. What we want is to get around this problem, which, I mean, can be done without the new formulation, but it can also be done with a new formulation. And a new formulation will allow us to actually see the world in a different way. All right, so let's take a concrete example. What about like f of x is equal to 4 minus x squared? So when we graph this function over here, it looks like this. It's up by 1, 2, 3, 4, and it opens downwards like so. Okay, so let's say we want to find at x equals 1, what is f of x? Well, we evaluate f of 1. 4 minus 1 quantity squared. 4 minus 1 is equal to 3. So 1 comma 3 is a point. 1, 2, 3 is a point on this curve right here. 1 comma 3. Now, suppose that is the point in which we aspire to find a tangent line to. Okay. How can we find a tangent line t to this point, 1, 3? Well, we have a point, and we need a slope if we want to use point slope form. The equation that says y minus y1 is equal to m times x minus x1. That's point slope form. Well, we need a slope. And we have a x1, y1. We need an x2, y2, because recall that the slope is y2 minus y1 over x2 minus x1. So we need another pair of points. Which pair of points should we pick? One guess, let's say idea number 1, is why don't we pick another point on this function? What about at x equals 2? What is the function at x equals 2? Is me plugging this 2 into our function f of x, which is 4 minus 4, which is equal to 0. So the point, say what? Question? No? Okay. So so notice that the point 2 comma 0, it can be our x2, y2. So let's try this right here. That's a point right here, right? At 2 comma 0. Here's another point. But notice if this is t, then if we find a line that goes through these 2 points, it's not going to be the same. Call it t1 for idea number 1. And notice that when we plug it into the slope formula, we get y2, which is a 2, minus y1, which is a 3, all over x2, which is a 0, minus x1, which is a 1. Yeah. So then notice that we get over here to -1 over -1, which is equal to 1. Hold on. y2, which is, oh yeah, no, this is right. y2 is 0, not 2. That was the x. y2 is 0. y1 is 3. Okay. x2 is 2. x1 is 1. So yeah, I had a feeling that was weird. So then this ends up becoming a -3 on the top and a +1 on the bottom. So this implies that our slope, m, is equal to a -3. And that's what our T1 is. It's a line of slope -3, but clearly it's not the same thing as a tangent line. This is the slope of the secant line. A secant line is is like a tangent line, but except going through one point and goes through 2 points on the function on the curve. So that idea doesn't work. So let's try to think of another idea. Okay, here's idea number 2. Well, if we don't want it to be all the way out here, why don't we just pick the same point? Why don't we take x1, y1 to equal x2, y2? Then, for sure, if that point is there and that point is there, then the secant line will contract to a tangent line, right? Should work, shouldn't it? Well, recall that slope formula is y2 minus y1 all over x2 minus x1. Notice that whenever, and remember that this is the point 2, 0, y2 is going to be 0 minus y1 is going to be a 0. x2 is going to be, 3 and 3 is what I mean. 3 minus 3 and 1 minus 1. Because we're saying that 1, 3 is equal to x1, y1. And same thing, 1, 3 is equal to our x2, y2. So I plug in 3, 3, 1, 1. What do we get here? 0 over 0, 0 over 0. What's wrong with that? Anything divided by itself is 1, right? Yeah, but, yeah, you guys say, yeah, but I think 0 is an exception, right? Is that what you guys think? It becomes undefined. You are correct that it's undefined, but why? Do you not know the reason? It's not your fault. None of your teachers tell you the reason. What do they tell you? And then move on. Don't ask questions, right? Don't ask any questions. Guess why? I'm about to show you why it's undefined. Mathematics has Boolean structure. Those of you who know how to code understand what Boolean means, right? Either or. So let's say I have a yellow piece of chalk. Guess what hand? Oh, I got closed both. Okay. Guess what hand the piece of chalk is in? If it's one piece of chalk, logically, it's either in my left hand or my right hand, right? Assume it's in one hand. Any of you pick a hand. Left. It's not in there. So what can you deduce for a 100% certainty? It should be here. Boom. Mathematics is created in this true or false structure. All mathematical statements are either true or they are false. That's that. We created math that way to function that way. Okay? So here's what happens if you assume a false statement. It's going to lead to more false statements. Let's assume 0 over 0 isn't undefined. Let's say it equals 1 because, you know, anything divided by itself should equal 1, right? Except for 0. But let's entertain the idea that 0 over 0 is equal to 1. If this is a flawed idea, it should lead to more contradictions. And here's what I mean. What if you assume that 1 is equal to 2? That's wrong, right? That's not true. But assume 1 equals 2. If I subtract the 2 from both sides, that means I get 1 minus 2, which is equal to 0. But that means I get negative 1 is equal to 0. A flawed assumption leads to more flawed assumptions because this is not true and this is not true. So if you make a flawed assumption up here, it's bound to lead to more flawed assumptions down here after algebraic manipulations, right? Here's another one, like 2 is greater than 3. Subtract the 3 from both sides, you get 2 minus 3 is greater than 0, but that implies that -1 is greater than 0. Is that true? No. So when you make a false assumption, it will only lead to more and more false assumptions. Let's assume this is true. If it leads to false assumptions, that means this was all itself a false assumption. This is called proof by contradiction. Well, if this is true, multiply both sides by 0. Then the zeros cancel here, and you get 0 is equal to 1 multiplied times 0. But that should equal 0, right? No flawed assumption at all. What if I subtract this term from both sides? I get 0 minus this 1 times 0. That should equal 0, right? Again, no flawed assumptions. 0 minus 0 is 0. Nothing going wrong there. What if I factor out a 0? Over here, what can I put? I'm going to put n. Over here, what can I put? I'm going to put this 1. Why do I say that? So what if you have 6x minus 3? What if I want to factor out a 3? Notice we pull out a 3, and this becomes 2x minus 1. Why is that true? It's because if I send the 3 back in, it restores the original equation. Why do I put an n here? Because n can be any possible number. And it will still restore this original equation. 0 minus 0 equals 0. N is any number. Any number possible. Because 0 times any number is. So this is appropriate factorization. But notice if I divide both sides by 0 here, what do I lead? I get n minus 1 is equal to 0 over 0. But by hypothesis, in our assumption, we assume 0 over 0 is equal to 1. So this means that n minus 1 should equal 1. If I add a 1 to both sides, what does that imply? If I add a 1 to both sides, what does that imply? N should equal 2. But that's a contradiction. Because n was any possible number. And you're saying it's only 2. But it can be pi, it could be 5,349, it could be negative square root of 37. Because any number times 0 is 0. That is why you can't divide by 0. Because it leads to logical flaws in mathematics. Just like when you assume 1 is equal to 2, it leads to more logical flaws. Dividing by 0 leads to logical flaws. Therefore, that's why you can't do it. And now you know. Feel free to rewatch this to try to digest it if it doesn't make immediate sense. So that's why dividing by 0 is bad. So that's why this idea number 2 is bad. So, idea number 3. Create new numbers. Why is this a good idea?
Because it gives you options.
Gives you options. Before, we knew what 3 minus 2 was, wasn't it? When we were very young. Well, what does this equal? 1. But some of your annoying teachers would probably say, but you can't do this one. 2 minus 3, you can't do it. Why? Because you didn't have the concept of a negative number yet.
Yeah.
You had to invent this new concept of a negative number, a number that goes in the opposite direction of the positives. Next, you knew how to do this division. What does this equal? But you did not know how to do this division. You didn't know how to do that. Just from whole numbers, you don't know how to do fractions. That's why they spend so much time teaching fractions to young kids, whatnot. So you had to invent the idea of a fraction. Here we invented the idea of negative numbers. Here we invented the idea of a fraction. What about square roots? What's the square root of 4? Plus or minus 2. But what's the square root of 2? This number is irrational. Like 1.4, some other stuff. 1.4, infinite amount of digits. Because it's an irrational number, it cannot be expressed in a finite amount of terms. We can only approximate it through more and more additions of terms. So this is an irrational number. So we went from the natural numbers to the integers to the rationals to the real numbers, which includes the irrationals. What happens after they ask you to take the square root of a negative 1? There is no real number whose square root is negative 1. Just like there's no real number such that when you multiply it times itself, it equals negative 1. There isn't one. Try 1. 1 times 1 is 1. That's not negative 1. Negative 1 times negative 1. Oh, but that's positive 1. We wanted negative 1. There is no real number that does that. So we had to expand to the complex number, to the complex plane, and say, the number that we need isn't on the real line, but surely it exists in abstract reality. You invent a new number. You say, let's just say that this is I. And let's talk about what are the consequences of that. So now you go from R to the complex numbers, C. Similarly here, we're going to create a new number to get past dividing by 0. We're not going to divide by 0. We're going to divide by an infinitely small number. What do we mean by infinitely small number? It means it is the closest number to 0 without being 0 itself. And such a number is called an infinitesimal. Okay, and this new number system, instead of R, it's going to be R star. Those are the reals. We're going to call these the hyperreals. Sounds cool, doesn't it? The hyperreals. It's actually really cool. Okay, let's call this infinitely small number, this infinitesimal, let's denote it as this letter omega, okay? Prior to defining this omega, let's talk about the transfer principle. This says that algebraic operations with infinitesimal numbers omega are the same as algebraic operations with normal real numbers. Omega is a hyperreal number. So what does that mean? Well, for instance, what about 7 plus omega minus the quantity 4 plus 3 omega? Well, what does this reduce to? Well, this is an infinitely small number. This is an infinitely small number. But because of the transfer principle, we can actually just treat it like any kind of algebraic label, like, you know, X or Y. We distribute that negative, and this is what we get. Then we combine like terms here and here. So we get, this becomes a 3 minus 2 omega. What about something like 5 omega plus 4 omega minus 13? Well, we just combine like terms to get 9 omega minus 13. Well, can we take binomial expansions of these infinitesimal numbers? Yes. It becomes this by definition. And this becomes 9 plus 3 omega plus 3 omega plus omega squared, which reduces to 9 plus 6 omega plus omega squared. Okay. Now, let's actually semi-rigorously define an infinitesimal number with an emphasis on semi-rigorously. Okay. An infinitesimal number h is a number such that, we got case 1, if h is a positive number, that implies for every real number that's part of the positive real numbers, r to the plus means positive real numbers, that this inequality holds. What does this mean pictorially? Well, it means here's our real number system. Over here is 0. R can be anywhere here. It can be here, it can be here, it can be here. It could be even really close to 0. This states that the infinitesimal h is the smallest possible real number, to the point where it is nearly indistinguishable from the number 0 itself, whilst still being distinct from the number 0 itself. It's still distinct from the number 0. It's infinitesimally small. It's the tiniest number you could think of. And then when you think of that number, smaller. And when you think of another number that's smaller than that, it's smaller, smaller, smaller. It's like trying to catch your shadow. Once you thought you caught the shadow, it moved on. So once you find a smaller number than your infinitesimal just scoots back. It will do this thing forever. Case 2, if your infinitesimal is a negative number, that implies that for every r, that's a negative real number, that this inequality holds. So drawing this picture out here, can everybody see what I draw over here? Can everybody see this right here? Is that blocking your vision? Okay, good. You guys can see it? Okay. So here's our 0 here now. This r can be here, it can be here, it can be here, it can be very, very small. But guess what? Our little h, our hyperreal infinitesimal, is even smaller than that. Matter of fact, if you keep changing r and make it smaller, h will always be able to get smaller than that number. So let's play this game. Pick of a small number. Someone pick a small number. I'll start. 0.1. What is the infinitesimal going to do? Give me a smaller number than 0.1.
0.001.
There you go. And then now I'm r. You're hyperreal h. I'm r. Oh yeah. You're 0.001. Well, I'm going to be 0.0001. Yes, that's right. It just moves. It's like, oh yeah, ooh. Oh yeah, ooh. Oh yeah, ooh. The hyperreal always wins the battle of being smaller. This is a very loose definition, but because you guys are fledgling mathematicians, this is what we're going to give you. So there's an interesting consequence of defining an infinitesimal number like this. Here's a theorem that will prove. Given an infinitesimal number h and a non-zero real number r, then here's a statement of the theorem. HR is itself an infinitesimal. Meaning R wasn't an infinitesimal before. It was just a positive real number like pi, positive pi, for instance. But when we multiply it times an infinitesimal number, it itself shrinks and becomes an infinitesimal number. What's a conceptual way of seeing this? Well, think about it. Guys, tell me, what's 3 times 4? 12. You guys know that. Boom, 12. Well, why is that true? Because if we call this thing 3, call this thing 4, chop it up into unit pieces, and create a grid out of it and extend these unit pieces, how many cells can you count? 12. Each of these unit cells, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's why 3 times 4 is 12. That visual picture is the reason behind it. Geometrical reason. It's an area. It's an area of 2 lengths. You multiply 2 lengths and you'll get an area. But now, what if I have R, a positive real number, and an infinitesimal? It's infinitely small. So what kind of area will it have? It just can't even have an area. It won't lift off of the line. You become an area once you lift off of the line to become an area versus a length. It won't even do it. It's so small. So when you multiply an infinitesimally small number times any non-zero real number, it itself becomes an infinitesimal number. Here's the proof. That's like the abstract way of thinking about it. Here's the actual proof. Okay, well, if h is infinitesimal and r is a non-zero real number, let k also be a non-zero real number. This is just shorthand for non-zero real number. Mathematical shorthand for non-zero real number. And I put this k is not equal to 0 to remind you of that fact, if you're not familiar with that notation. See, I had it here as well. So this means r could not have equal to 0 in this situation as well. So recall that we have k now, non-zero real number. I'm just going to say let k be a non-zero real number. And again, from hypothesis, let r be a non-zero real number. Okay. What is K over R then? If I take a non-zero positive real number and divide it by a non-zero positive real number, what do I get? Another non-zero positive real number, right? Because you divide a positive number by a positive number, that fraction, that ratio should be another positive number. So the ratio R over K is also a positive real number, and it's non-zero. It's non-zero because the numerator wasn't zero. And it's defined because the denominator can never be zero, so we're not dividing by zero. Okay? Notice that if this is a positive, non-zero real number, and h is assumed to be an infinitesimal, then by the definition of an infinitesimal number, this inequality holds. By definition of infinitesimal. This is the whole pick a really small number. Infinitesimal is just going to be like, well, I'm to the left of you, but I don't touch zero ever. But I'm always to the left of you, but I don't touch zero ever. Okay? Notice that when we multiply both sides of this inequality by r, we get 0 times r, which is 0, hr here, and the r's in the denominator cancel out. K is just an arbitrary positive real number. And this shows that hr is satisfying the definition of an infinitesimal number. Just replace h here. This is hr, and replace r here with a k. It is exactly what's over there. You guys see that? So we've proven that the product of a non-zero real number with an infinitesimal number is itself an infinitesimal number now. So HR is an infinitesimal number. We proved this right here. So you guys don't have to know how to do this proving stuff. You will be expected to remember that the product of an infinitesimal number with a non-zero real number is itself an infinitesimal number. That's what you need to take away from this. If you would like to understand the proof, then I highly encourage you to do that. But I will also be frank with you and tell you that it is not necessary for you to understand this proof for this class. But I encourage you to understand it because it'll give you a deeper understanding of what we're talking about. So, what's the point of all this stuff? Well, this just goes to show you that there's levels to reality and there's levels to numbers because numbers allow us to quantify reality. What do I mean by levels to reality? Sounds like I'm, one of those weird people. Bruh, there's levels to reality, man. You guys hear people talking like that sometimes?
Yeah.
Yeah. Your uncle talks like that? Well, wow. Well, looks like your uncle is not wrong when it comes to the real numbers. The hyperreal numbers are actually inside the real numbers. We just never knew it because we never invented them. And because we never invented them, we never knew that they were there, but they are there. The hyperreal numbers omega take a look right here. They exist right here and right here. Where here's 0, here's omega, here's 2 omega, and here's 3 omega, and so on and so forth. Negative omega, negative 2 omega, negative 3 omega, and so on to infinity, ad infinitum. So What does this mean? What does this thing that I put up on the board even mean? Well, it means that just like the real numbers are infinite, this goes out to positive infinity over here, this goes out to negative infinity over here, right? Just like the real numbers are infinite, squished infinitely tight to 0, right here and right here, squished infinitely tight is this section right here. This section right here, all of this section, and this is infinite as well. All of this fits right here where that orange dot is, to the right of 0. And all of this stuff fits right here where that orange dot is, to the left of 0. So, because we've invented these new numbers, we now realize that this is the hyperreal level, the omega, the infinitesimally small level. It's actually been in front of us all along when we just didn't know it. Why do we not know it? Because we had not imagined it before. How could you know something is there if you don't have a concept for it? Right? Especially for numbers. Because what are numbers? Do numbers exist in real life? Or are they just a figment of our imagination, something that human beings have invented to quantify reality? I have 2 pieces of chalk. I have 1 jug. I have 1 picture of one of the best mathematicians of all time, Leonhard Euler. Right? Human beings invented this stuff to keep track of things, you know? So do they exist? Are they real? Are numbers real? Can you smell a number? Can you eat a number? Can you lick a number? Are they real?
I want to say to a certain extent. Yeah. I say yes, but no.
You're not wrong. This is really a philosophical question that, for all we know, there is no answer to this question. Are numbers real? There's really no answer to this question. Numbers might be our way of understanding the actual structure of space and time. But that does not mean that they are part of space and time. But it could mean that they are. I kind of think that they are, but that's my opinion and I can't prove it, not yet. So, what do we mean by this? We mean that this omega level is a infinitesimally small level that fits right here. All of this infinitely long line of infinitely small infinitesimal numbers fits right there. Just like the negative version of that, infinitely long, infinitely far, fits all the way right here. We have been looking at it all along, but we haven't noticed it. Take a look at your arm. Do you guys see squamous cell epithelial cells? Do you see adipose cells? Do you see myofibrils? Do you see histone beads? Do you see sodium-potassium pumps? Do you see voltage-gated ion channels? No, but they're there and they're inside our cells. And we've invented new technology and microscopes to be able to zoom in where our eyes can't see. That's exactly what's going on here with the hyperreal numbers. Someone invented them in 1960. And then we realized that, oh, technically they've been there all along and we just didn't notice them. And we're going to use them to develop calculus. So the entire omega level The entire line fits around the point 0. The book likes to say at the point 0, but that's technically not true. It's around the point 0. They just say that to make you realize that you can approximate it at the point 0 because it's so tiny. This chalk that I put here is still, that's not a fair description of how tiny it is because it's so thick of a piece of chalk. I would have to put such a small piece of chalk that you wouldn't even be able to see that there's a dot there at all. That makes sense. I think I've hammered that concept. In as much as I can now. We'll have to deal with it and think about it more and more as we go. Okay? So, if omega is an infinitely small number, what happens when you multiply it times itself? It what? It would get even smaller?
Well, I mean, you're already close to 0 and it's getting lower, so it has to be, something has to be smaller than omega.
Think about it like this. 1 over 100. That's 0.01, right? That's a small number, isn't it? Okay. What if I multiply this number times itself? 1 over 100 times 1 over 100. Let's see if it gets bigger or smaller. Well, the denominator becomes 1 over 1, 2, 3, 4. Notice that this is the same thing as 0.1, 2, 3, 1, 2, 3, 4. Boom. I put 0, 1. Right, because 1, 2, 3, 4. Yep. Notice that I got even smaller. One, two, three, four. Let me make sure. 1, 2, 3, 4. Oh, I'm going the wrong way. Put the decimal here. 1, 2, 3, 4. 1, 2, 3, 4. Yep. Or actually, I went the 1. Boom. Yes, I had it right. I was just making sure. Notice it got smaller. Did it not? So when you multiply a small number times itself, it gets even smaller. It gets even smaller. So guess what? There's an omega squared level. And guess what? The omega squared level, where this is omega squared, this is a 2 omega squared, this is a 3 omega squared, this is a negative omega squared, this is a negative 2 omega squared, this is a negative 3 omega squared. All of this infinite amount of omega squared fits right up right here to the right of the omega level. The whole line. And the whole line here fits right here, barely to the left of the omega level, 0. So there's levels. This is infinitely small, but this is infinitely, infinitely small. Guess what? There's a infinitely, infinitely, infinitely many small. What would we call this level? Yeah, the omega cubed level. That's right. Yeah. Think about it. These are the consequences of inventing an infinitely small number. if you now multiply an infinitely small number times another infinitely small number, the consequence of creating such a beast, such a crazy number system, is when you multiply it times an infinitely small number, it gets even smaller. So not only was it infinitely small, their product is now infinitely times as infinitely small. So where does the square root of omega fit in all this? So notice, to answer this question, what is the square root of omega squared? Yeah, technically plus or minus omega, but we'll take the principal square root. So notice omega squared, when we square rooted it, brought it up a level. What happens when we square root omega? It's going to bring it up to this level right here, halfway between the reals and the omega level is the square root omega level. Make sense? You could think of it as this being omega to the 1 power and this being omega to the 1/2 power. So what if I took the cube root of omega? Where would it be? You're pulling it up higher. Absolutely right. This would be omega to the 1/3, which is the same thing as the cube root. So over here, this would be the omega cube root of omega level. Okay. We have not gone over this whole section yet, and class time has hit beyond its limits. So what we will be doing is, Monday there is no class, but I'll upload, instead of what I have on the syllabus 1.2, I'll put a continuation of 1.1. As I said, the schedule is tentative, so that's just how it goes. I don't mind spending a long time with the fundamentals and then revving up later, rather than going through the fundamentals really fast and then halfway through the semester nobody gets what's going on. I'd rather have a slow start and a fast finish than a fast start and we don't even run past the finish line because we fell over and we twisted our ankles. You know what I'm saying? So now what you guys need to do is immediately get access to the syllabus via Canvas and start reading section 1.1 or 1.0. It's technically called 1.0. Or no, it's actually called 1.1. Never mind. Some of my classes do that. Some of my textbooks don't. Start doing that and I will assign homework as well.
Those will be uploaded onto Canvas?
Yes, everything is off of Canvas. Let me know if you guys have any questions with Canvas or accessing the material.
Have a good night.
You too. You guys at home, any questions so far?
Yes, sir. Yeah, Professor, can you hear me?
Yes, I can hear you.
Awesome. How have you been?
Good, how are you?
I'm good. I'm doing a lot better.
Wonderful.
COVID is not fun.
Yeah, it's really strange.
I got it. It was not fun at all.
Oh, okay. Well, at least you're now you have some immunity to it.
What is it, like 3 months or something?
I don't know, but you have immunity to it, so.
Yes, sir. Hey, I have a question.
Yes, sir.
Yesterday was like the first lab. Was this supposed to be like a everything thrown in your face type of day?
I wasn't there, so I don't know what happened.
Professor Zoller kind of just like threw everything at our faces and made us like act really fast. And I'm like, okay.
Was he talking about this stuff that I'm talking about?
No.
What was he
No.
talking about?
He just went, he told us how to install Maple, and that was
Oh,
gonna be
okay,
like
okay.
how we use our labs. And it took me a while to download because my computer software is a little different. But then other
I
than
see.
that, it wasn't that bad. I mean, he just
Okay.
like told us like, okay, this is what you're gonna be doing, like to solve and all this. And I'm just like, okay, this is a lot of information, but I mean, it's all
Yeah.
right though. But
Yeah.
we took an assessment, and that was pretty tough. But other than that, like that's just it's not for a grade, so that's just assessing where we're at. So with this class, I think it'll be good for me just to like get it all down.
Yes. This class will be very fun.
I bet, man. I'm ready for
Yes.
it.
I mean, look at this stuff, man. Like, this is really cool stuff. Like,
We went to
this
the
is
simplest
really,
like level.
yeah, levels to real
We went
numbers and
all the way
levels to
down to
reality.
like we went all the way down to like omega square root.
Yes. Oh, it gets even better. I'll give you a preview. There's levels above as well as levels below. So
Yeah.
we'll
Did we
talk
miss
about that.
I have another question. Did we miss anything because we kind of like came into the Zoom meeting just a little bit late?
I don't think you missed anything.
Yeah.
Clearly, if you did, you could rewatch it because I'm going to
Yeah.
upload this. So you'll be able to see it from the beginning of the recording.
Okay.
That way you can see if you missed anything. This is all stuff in the book, but I believe I'll be able to explain it to you better than the book can. So
Yeah.
read the book, though. It's very important. The author does a very good job of trying to explain it well. So
You got it. Appreciate you, sir. Thank you.
all right. Have a good day.
You
See
too.
you next time.
Yes, sir. See you then.
Goodbye.